Okay, let's unpack this. Have you ever really stopped to think about what makes up, well, everything around you?
Yeah, I mean, not just what it is, but how its fundamental nature dictates all the chemistry we see.
Exactly. Welcome to the deep dive. We take your source material, like today's textbook chapter, and really distill it down.
Get to the core nuggets of knowledge for you.
Right.
And today, our mission, really for you, our listener, is a foundational deep dive. We're digging into inorganic chemistry.
Kicking things off with the first chapter of Shriver and Atkins Inorganic Chemistry, the 5th edition.
A real bedrock text. It helps you wrap your head around the periodic table, element behavior, all that good stuff.
And we'll break it down step by step. The goal is to make these complex ideas pretty clear, even without having diagrams in front of you.
Exactly. We want to help you build this strong mental model of atoms.
From their cosmic beginnings, way back, to their internal structure and the properties that make each element unique.
Get ready for some of those aha moments, hopefully. Connecting dots you might not have seen before.
Giving you that powerful lens to view the chemical world.
Okay, so if we're going to understand the elements, where else do we start? But the very, very beginning.
The birth of the universe itself.
Precisely. The current thinking is, what, about 15 billion years ago? The Big Bang?
Hard to even picture.
Oh, absolutely. Temperatures were just scorching, 10 to the 9 Kelvin. Particles had way too much energy to stick together.
Right.
But as the universe expanded, it cooled. And forces started to, well, take hold.
Like gravity?
Gravity played a role, but first, the strong force. It's incredibly powerful, but only acts over tiny distances.
Okay.
It pulled protons and neutrons together, forming the first atomic nuclei.
The cores of atoms.
Exactly. Then, the electromagnetic force, weaker but longer range, came into play. It bound electrons to those nuclei.
Forming the first actual atoms.
That was it, the true dawn of chemistry, right there.
So these first particles, for chemistry, which ones do we really need to focus on?
Yeah, good question. For chemistry, we really zone in on electrons, protons, and neutrons.
The big three.
Pretty much. And every element is defined by its atomic number, Z. That's simply the number of protons. Non-negotiable.
That's its identity.
That's its identity. But an element can have different versions, different isotopes.
Okay, what's the difference there?
Same number of protons. So it's the same element, but a different number of neutrons.
So they weigh differently.
Exactly. That gives them a different mass number, A, which is just protons plus neutrons.
Can you give an example?
Sure, think hydrogen, normal hydrogen. 1 proton, 0 neutrons. Then there's deuterium, 1 proton, 1 neutron.
Heavy water uses that.
It does. And then tritium, 1 proton, 2 neutrons. All hydrogen, but different isotopes, different mass numbers.
It's amazing that these tiny things started it all. But how do we get from hydrogen and maybe helium to everything else? Gold, carbon, oxygen.
Yeah, how do we get that incredible diversity? That's where nucleosynthesis comes in. The cosmic element factory.
In stars, right?
Primarily, yes. The very first stars formed from these huge clouds of mostly hydrogen and helium.
It's gas collapsing.
Basically, yeah. Gravity pulls it all together, compressing it, heating it up like crazy. Immense temperatures, immense densities at the core.
Hot enough for.
Hot enough to spark fusion reactions, nuclei literally smashing together and merging to form heavier ones.
And that releases energy.
Oh, enormous amounts of energy, millions of times more than a chemical reaction, because that strong force holding the nucleus together is just so incredibly powerful.
Wow. So stars are basically giant element factories. Burning hydrogen into helium, helium
into carbon, oxygen, all the way up to iron, which has atomic number 26.
Z equals 26.
Right. These processes are often called nuclear burning. It's not fire like we think of it, but fusion.
And you said up to iron. Why does it stop there? Sort of.
Great point. Elements up to iron and nickel are super abundant because their nuclei are the most stable. It's all about binding energy.
Binding energy. That's like the glue holding the nucleus together.
Kind of, yeah. It's the energy difference between the nucleus and its separate protons and neutrons. Iron 56 sits right at the peak of this binding energy curve.
Meaning it's the most tightly bound, hardest to break apart.
Exactly. Making elements heavier than iron via fusion actually starts to cost energy instead of releasing it. So stars can't easily do it that way.
Okay, so then, where do the really heavy elements come from? Gold, lead, uranium.
Those need even more extreme conditions. Often things like neutron capture followed by beta decay.
Neutron capture. Sounds straightforward enough.
Well, imagine a nucleus just soaking up free neutrons, getting heavier and heavier. But neutrons don't change the element's identity, remember?
Right, that's the proton number.
Exactly. But eventually, the nucleus becomes unstable, and it undergoes beta decay.
What happens then?
A neutron inside the nucleus essentially transforms into a proton and ejects an electron that's the beta particle.
So the mass number stays roughly the same, but you get an extra proton.
You got it. And an extra proton means?
A new element. One step up the periodic table.
Precisely. That's how we think many heavy elements are built, often in really dramatic events like supernova explosions or colliding neutron stars. Insane amounts of neutrons flying around.
That's incredible. Thinking about element creation, wasn't there an element technetium that was important in medicine? Was that made in space?
Ah, good connection. Technetium Z43 is interesting because it was actually the first element made artificially, synthesized in a lab.
Oh, not naturally occurring.
It has no stable isotopes,
Yeah.
so any primordial technetium decayed away long ago. Finding it filled a gap Mendeleev predicted in his periodic table.
And its use in medicine.
Right. Its isotope, technetium 99 meter, is a workhorse in nuclear medicine. It emits gamma rays, which we can detect outside the body, and it has a short half-life, just over 6 hours.
Ideal for imaging then.
Yeah.
Doesn't stick around too long.
Exactly. Which brings us nicely to human-controlled nuclear processes. Nuclear fusion and nuclear fission.
Fusion, we talked about light nuclei merging. Fission is the opposite.
Right. Fission is splitting heavy nuclei, like uranium, into lighter ones. Also releases a ton of energy.
That's nuclear power.
That's the basis of it, yes. Huge energy output, about 200 MeV per event, but it comes with challenges like managing radioactive waste.
Okay, so elements are forged in stars, sometimes in labs, but it all boils down to protons, neutrons, electrons. How do they arrange themselves inside the atom?
Right, let's zoom in. The simplest case to start is hydrogenic atoms.
Hydrogenic, meaning like hydrogen.
Like hydrogen, yeah, or any atom or ion with only one electron left. Helium ion, lithium 2+ ion.
Why start there? Seems a bit specific.
It removes the complication of electrons repelling each other. Let's just get the basic rules down first. Our understanding here really jumped forward thanks to spectroscopy.
Studying light, you mean?
Exactly. When you energize hydrogen gas, say, with electricity, it glows. But not like a smooth rainbow.
No.
No, it emits light only at very specific colors, specific frequencies. These fall into distinct series: Lyman, Balmer, Paschen.
I remember seeing those lines in labs.
Yeah. And a scientist named Rydberg found a mathematical formula connecting these wavelengths using simple whole numbers. It was a huge clue.
A clue about what?
That electrons couldn't just be anywhere. They could only exist in specific energy levels. Discrete steps, not a smooth ramp.
So electrons aren't orbiting like tiny planets, then?
Yeah.
In any old path?
Not at all. That old Bohr model was a useful step, picturing orbits, but it wasn't the full story.
Huh?
The spectra made sense if electrons jumped between these specific levels, absorbing or emitting energy as photons, packets of light.
And the energy of the photon matched the energy difference between the levels.
Precisely. Bohr's model got the formula right for hydrogen, but it took quantum mechanics, Schrödinger, and Heisenberg to really explain why.
You mentioned sodium street lamps earlier. Is that the same principle?
It is. A perfect everyday example.
Yeah.
Excite sodium atoms with electricity, electrons jump up energy levels.
And when they fall back down?
They emit photons. For sodium, the most common jump produces that characteristic yellow light. It's a direct result of these allowed energy levels.
Okay, so quantum mechanics changed the game. What were the big ideas?
Well, a couple of really weird but fundamental ones. De Broglie suggested wave-particle duality.
Electrons are waves and particles.
Yep. Weird but true. They have wave-like properties, which leads straight to Heisenberg's uncertainty principle.
Can't know position and momentum at the same time.
Exactly.
Yeah.
The more precisely you know one, the less precisely you know the other. It's fundamental.
And Schrödinger.
Schrödinger developed his famous equation. It uses a mathematical function, the wave function, to describe the electron's behavior.
Like a blueprint for the electron's wave.
Sort of, yeah. And the crucial thing is, physically meaningful solutions to his equation only exist for specific, discrete energy values.
Ah, so the math itself forces the energy levels to be quantized.
Exactly. It's not just an assumption anymore. It comes out of the core theory.
So this wave function, what does it tell us about where the electron actually is?
According to Max Born, the square of the wave function, check, gives you the probability density.
Probability, not a definite location.
Nope. It tells you the likelihood of finding the electron at any given point in space. High thought, high probability.
If thought is 0.
That's a node. 0 probability of finding the electron there, like absolutely none.
Wow.
And like any wave functions have phases positive and negative parts. When they overlap, they can interfere.
Add up or cancel out.
Right. Constructive interference boosts the probability. Destructive interference cancels it out. This is absolutely key for understanding chemical bonding later on.
Okay, so these wave functions, they basically are the atomic orbitals we talk about.
That's exactly right. An atomic orbital is a wave function for an electron in an atom, and we label them using quantum numbers.
The electron's address system.
That's a good way to think of it. There are 3 main ones defining the orbital itself.
Okay.
First, n, the principal quantum number, tells you the main energy level and roughly the size. Higher n, higher energy, bigger orbital. Think shells like 1, 2, 3.
Got it. A sec.
Orbital, the orbital angular momentum quantum number. This dictates the orbital shape. For a given n, L can go from 0 up to n1.
And third.
ML, the magnetic quantum number. This specifies the orbital's orientation in space. It can range from mellow through 0 to plus L.
So the letters we use, S, P, D, D, F, how do they fit in?
They correspond directly to the value of L. L or 0 is an s orbital, spherical.
Okay.
Lm gives you p orbitals, dumbbell-shaped. L over 2 gives d orbitals, more complex shapes. L3 gives f orbitals, even more complex.
And for each L, there are different LEL values, right? Different orientations.
Exactly. For LO1 p orbitals, LL can be -1, 0, +1. That gives you 3 p orbitals, px, pi, pz, oriented along the axis.
And for D orbitals, L2.
ML can be -2, -1, 0, +1, +2. So you get 5 d orbitals with different shapes and orientations.
Okay, that makes sense. N is the shell, L is the subshell in shape, ML is the specific orbital orientation.
You got it. All orbitals with the same n form a shell. All orbitals in a shell with the same L form a subshell.
That's 3 quantum numbers. Is there a 4th one? Something about spin.
Ah, yes. Crucial detail. Electron spin. Electrons have this intrinsic angular momentum like they're spinning.
But they're not actually spinning like tiny balls, are they?
No, it's a purely quantum mechanical property. But it behaves like angular momentum. It's described by 2 more numbers, s, which is always 12 for an electron, and m's, the spin magnetic quantum number.
And M's can be.
+12 spin up, or -12 spin down.
So every electron in an atom needs 4 quantum numbers to be fully described. N, L, ML, and MS.
That's the complete address. N, AOET, ML define the orbital. Ms defines the electron's spin state within that orbital.
Going back to orbitals, you mentioned nodes, places the electron can't be.
Right. Regions where the probability is 0. There are 2 types.
Okay.
Radial nodes are spheres at certain distances from the nucleus. The number depends on N and L. It's NL1.
And the other type?
Angular nodes are planes or cones going through the nucleus. The number of these is the quantum number L.
So S orbitals with L0 have no angular nodes.
Correct. That's why they're spherically symmetric.
Yeah.
P orbitals, L1, have 1 angular node, a plane splitting them into 2 lobes.
And D orbitals, L2, have 2 angular nodes, giving those cloverleaf shapes.
Generally, yes. These shapes aren't just pretty pictures, they're fundamental. The boundary surface shows where you have, say, a 90% chance of finding the electron.
And you mentioned something about the nucleus earlier.
Yes, critically important. Only s orbitals have a non-zero probability at the nucleus.
P, D, F orbitals have a node there.
They do. Electrons in p, d, or f orbitals are never found precisely at the nucleus. This affects how strongly they feel the nuclear charge.
How so?
Well, we also look at the radial distribution function, PR. It tells you the probability of finding the electron at a certain distance r, summed over all angles.
So not just at a point, but in a thin shell at distance r.
Exactly. For a 1s orbital in hydrogen, this peaks at the Bohr radius, 52.9 picometers. That's the most probable distance. For 2s, the peak is further out.
Okay, I think I'm getting the picture for 1 electron. But most atoms have many. How does that change things?
Right, now we add complexity. The Schrödinger equation gets really hard to solve exactly. But we can still use the orbital concept as a very good approximation.
So we still talk about 1s, 2p, through it orbitals.
We do. But now we need rules for filling them. The most fundamental is the Pauli exclusion principle.
No 2 electrons can have the same address.
Exactly. No 2 electrons in an atom can have the identical set of all 4 quantum numbers. N, L, ML, MS.
Which means an orbital, defined by N, L, and ML, can hold how many electrons?
A maximum of 2. And if it holds 2, their spins must be opposite. One spin up, plus 12. One spin down, -12. Paired spins.
Okay. And how do these multiple electrons affect each other? They must interact.
Oh, absolutely. They repel each other, big time. This repulsion effectively shields an electron from the full positive charge of the nucleus.
So an electron doesn't feel the full Z protons.
Not usually, no. It feels a reduced charge, which we call the effective nuclear charge, ZEF.
And the difference between Z and ZEF is due to this shielding by other electrons.
Precisely. Electrons in inner shells are very effective at shielding outer electrons. But even electrons in the same shell shield each other somewhat.
Does the orbital shape matter for shielding?
Yes, significantly. Remember how Alcala's orbitals have probability at the nucleus, but PDF don't?
Yeah.
S electrons can penetrate closer to the nucleus, past some of the inner shielding electrons.
So they feel a stronger pull, a higher ZEF?
Exactly. S electrons penetrate better than P, which penetrate better than D, which penetrate better than F.
And this affects their energy levels.
Profoundly. In many electron atoms, unlike hydrogen, orbitals within the same shell are not degenerate. They don't have the same energy.
Because of penetration and shielding.
Correct. The energy order is generally Ns, N, P, N, D, N, A, F.
S orbitals are lowest in energy within a shell because they're least shielded.
Right. They feel the highest ZEF. F orbitals are highest in energy because they penetrate the least and are most shielded. This explains the filling order we see.
Like in lithium, the third electron goes into 2s, not 2p.
Exactly, because 2s is lower in energy than 2p due to better penetration.
So is there a standard blueprint for filling these orbitals as we add electrons?
There is. It's called the building up principle, or sometimes the Aufbau principle. It gives the general order of orbital occupation.
Which is?
1s, then 2s, then 2p, 3s, 3p, then crucially, 4s before third, then 4p, 5s, forward, and so on. You can follow it on the periodic table.
That 4s before third always seemed a bit odd.
It comes down to that penetration effect again. The 4s orbital penetrates enough to dip slightly below the third orbitals in energy, at least initially.
Okay, and each orbital takes 2 electrons. What about when you have multiple orbitals at the same energy, like the 3-2p orbitals?
Ah, good point. That's where Hund's rule comes in.
Hund's rule.
It says that when filling degenerate orbitals, like the 3p orbitals or 5d orbitals, electrons will occupy them singly with parallel spins, all spin up for instance, before any orbital gets a second electron with a paired spin.
So spread them out first, keep spins aligned. Why?
It minimizes electron repulsion. Electrons are negatively charged. They want to stay apart. Having them in separate orbitals with parallel spins is energetically favorable. It leads to extra stability for half-filled subshells, like in nitrogen.
Nitrogen is 1 spart, 2 isetch is 2p house.
Right, and those 3 2p electrons are in separate p orbitals, all with the same spin, AFL.
Now, this building up principle, does it always work perfectly?
Mostly, but chemistry loves exceptions, particularly with D and F block elements.
Like chromium and copper.
Exactly. Chromium should be R3DO 4 sets, but it's actually R3DO 4 sets.
It promotes a 4's electron to third. Why?
To get that half-filled D subshell, it's surprisingly stable, same idea for copper. It should be R3DO 4 sets, but it's actually R3DA's 4 sets.
To get a completely filled D subshell.
Yeah.
Also very stable.
Precisely. It's all about achieving the lowest possible energy state, minimizing repulsions, maximizing stability.
And quickly, what about ions? Especially those transition metals, the D block, when they lose electrons.
Right. Important point for D blocations. When forming positive ions, electrons are removed from the outermost LS orbital first, like the 4s, before any electrons are removed from the D orbitals, like the third.
Even though 4's filled before third.
Yes. Once the D orbitals start filling, the relative energy shifts slightly. So for ions, it's always outer S electrons out first. Makes things a bit simpler, actually. Ion is R3DO, not R3DO 4 city orbitals.
Okay. So we've built the atoms, electron by electron. Now, how do we use all this to understand how elements behave and how we classify them?
Well, the broadest classification is metals, nonmetals, and metalloids, based on general properties.
Shiny versus dull, conductive versus insulating.
Right. Metals usually shiny, malleable, conductive. Nonmetals often gases, liquids, or brittle solids, poor conductors. Metalloids like silicon, germanium, are somewhere in between. Useful, but coarse.
The real key is the periodic table, isn't it?
Absolutely. Mendelev's stroke of genius, organizing elements by increasing atomic number, but arranging them so elements with similar chemical properties fall into vertical columns, the groups.
And the table's layout directly reflects the electron configurations we just talked about.
Exactly. The blocks S, P, D, F tell you which subshell is being filled. S block on the left, P block on the right, D block in the middle, F block usually pulled out below.
And the rows, the periods.
The period number corresponds to the principal quantum number n of the outermost, or valence shell being filled. Period 1 fills N11, period 2 fills NO2, and so on.
And the group numbers relate to valence electrons.
Generally, yes, especially for the S block and P block, main groups. Group 1 has 1 valence electron, Group 2 has 2, S7, Group 13 has 3, Group 17 has 7, Group 18 has 8.
So the table is literally a map of electron structure.
It is. And because structure dictates properties, we see predictable periodic trends in things like size, ionization, energy, etc.
Okay, let's break those down. Starting with size. Atomic and ionic radii. How does size change?
Two main trends. Atomic radius generally increases as you go down a group. You're adding entire new electron shells, higher n. The outermost electrons are simply further from the nucleus, more layers.
Makes sense. And across a period, left to right.
It generally decreases across a period.
Decreases, even though you're adding electrons.
Yeah, seems counterintuitive, but think. You're adding protons to the nucleus too, so Z, the nuclear charge, is increasing.
Pulling the electrons in tighter.
Exactly. Within the same shell, the increasing nuclear charge wins out, pulling the electron cloud closer, so atoms get smaller across a period.
What about ions? Cations and anions?
Cations, positive ions, are smaller than their parent atom. You've lost electrons, often the entire outer shell, and there's less electron repulsion.
And anions, negative ions.
Anions are larger than their parent atom. You've added electrons, increasing repulsion, making the electron cloud expand.
Are there any major bumps or exceptions in these size trends?
The big one is the lanthanide contraction.
Lanthanide contraction.
Yeah.
Sounds important.
It is. Look at the D block elements in period 6, starting with hafnium, HF. They are unexpectedly small, almost the same size as the elements directly above them in period 5, like zirconium, Zir.
Why? They have an extra shell. Should they be much bigger?
You'd think so. But remember, the F block elements, the lanthanides, are squeezed in before them. They're filling the 4f orbitals.
And orbitals are bad at?
Shielding. They're terrible at shielding the outer electrons from the increasing nuclear charge.
So the valence electrons in hafnium and beyond feel a much stronger pull than expected.
A much higher Zeph, yes. It contracts the atom, counteracting the effect of the added shell. It has huge knock-on effects for the chemistry of those heavier elements.
Fascinating. Okay, next property. Ionization energy, the energy to remove an electron.
Right. The first ionization energy, I1, is the minimum energy to pluck the outermost, least tightly bound electron from a gas phase atom.
Where is it highest and lowest?
Generally, it's lowest at the bottom left of the table. Think cesium or francium, big atoms, low Zeph, easy to remove that outer electron.
Make some reactive metals.
Very. And it's highest at the top right, helium, neon, small atoms, high Zeph, electrons held very tightly.
Noble gas is very unreactive.
Exactly. The trend mirrors atomic size and Zeph. Smaller size, higher Zeph, means higher ionization energy.
Are there smaller wiggles in the trend across a period?
Oh yeah. Look at period 2. Boron actually has a lower I1 than beryllium, even though boron is further right.
Why is that?
Beryllium is removing a 2s electron. Boron is removing a 2p electron. That 2p electron is slightly higher in energy and better shielded than the 2s, so it's a bit easier to remove.
Stability of filled versus starting to fill subshells. Same thing between nitrogen and oxygen.
Exactly. Nitrogen has that stable half-filled bulk configuration. Oxygen is pair, so removing one electron gets it to that stable half-filled state, making it slightly easier than removing one from nitrogen.
What about removing more than one electron? Second, third ionization energies.
Successive ionization energies, I1, I2, I3, always increase. Always harder to remove an electron from a positive ion than a neutral atom.
And sometimes there's a huge jump.
Big time. If removing the next electron means breaking into a stable, filled inner shell, a noble gas core, the energy cost skyrockets. Try taking a second electron from sodium. No, you're breaking into the neon core. Very difficult.
Okay. How about the opposite, gaining an electron? Electron affinity.
Electron affinity, EA, is the energy change when a gas phase atom gains an electron. It's often released, exothermic, negative value, but not always.
Where is it most favorable? Who wants electrons the most?
Generally highest, most negative EA, for elements near fluorine, halogens, group 17, and oxygen sulfur, group 16.
Why them?
They have high Zeph and room in their valence shell to accept an electron, often achieving a stable filled or half-filled shell. Adding an electron is energetically favorable.
Who doesn't want electrons? Low electron affinity.
The noble gases, obviously their shells are full. Also, elements like beryllium or magnesium, group 2, the incoming electron would have to go into a higher energy p subshell. And nitrogen, group 15, adding an electron disrupts that stable, half-filled p subshell, requires energy input, positive EA.
Got it. And finally, electronegativity. How is that different from electron affinity?
Good question. Electron affinity is about an isolated atom gaining an electron. Electronegativity is about an atom's power to attract electrons to itself when it's in a chemical bond, part of a compound.
So it's about tug of war for electrons within a molecule.
That's a great analogy. It generally increases across a period. Higher Zeph, smaller size, pulls electrons better, and decreases down a group. Electrons further out, less pull.
So fluorine is the champ, top right.
Fluorine is the most electronegative element, smallest halogen, highest Zeph for its period, followed by oxygen, nitrogen, chlorine. The metals on the bottom left, like cesium, are the least electronegative. They tend to give up electrons easily.
And different scales exist to measure this. Pauling, Mulliken.
Yes, different ways to calculate it, based on bond energies or on ionization energy, on electron affinity, Mulliken, or Zeph and radius, Allred, Rochow. They all show the same general trends. It's hugely useful for predicting bond type, ionic, polar covalent, nonpolar covalent.
And one last related term, polarizability.
Right. Polarizability is different again. It's how easily an atom's or ion's own electron cloud can be distorted or squished by an external electric field, like from a nearby ion.
So not pulling other electrons, but having your own cloud pushed around.
Exactly. Who do you think is more polarizable, a big atom or a small one?
Bigger. Electrons are further out, held less tightly.
Precisely. Large atoms, and especially large anions, like iodide, iodo, are highly polarizable. Their electron clouds are diffuse and easily distorted.
And small atoms, like fluorine.
Very low polarizability. Small, tightly held electron clouds. Cations are also generally less polarizable than anions.
And this matters for bonding, too.
Oh, definitely. A highly polarizing anion cation, small, highly charged, next to a highly polarizable anion, large, maybe highly charged, can distort the anion's cloud so much that the bond gets significant covalent character, even if you'd expect it to be ionic. Phasion's rules help predict this.
Wow, okay, what a journey. From, like, the Big Bang, stars, forging elements.
Right, through quantum mechanics, orbitals, electron configurations.
To understanding why the periodic table looks the way it does and how these properties like size and electronegativity emerge, it all connects.
It really does. We've covered nucleosynthesis, the rules governing electrons, quantum numbers, Pauli, Hund, and how they manifest as these observable periodic trends. Each piece builds the picture.
So for you listening, what's the big takeaway? You now have this framework, this mental toolkit.
For making sense of the periodic table, predicting properties, understanding why chemistry happens the way it does.
Right, some reactions go and others don't. When materials have the properties they do, it's foundational.
We really hope this deep dive has brought some clarity, maybe a new appreciation for these fundamental building blocks.
Yeah, thanks so much for joining us on this exploration.
From the deep dive team, keep digging for that knowledge.
And now, maybe a final thought for you to chew on. Given this delicate balance of forces, quantum rules, shielding, penetration, all dictating atomic properties, what surprising connections might you find between these fundamental characteristics and the complex chemical reactions or material properties that shape our world?